Have you ever wondered how an AI really thinks? You know, how it goes from looking at a ton of data to making a specific call. Well, it's not magic. It's actually math. And the real secret sauce is these tiny, hidden decision makers tucked away inside the network. So today, we're going to pull back that curtain and really get into what these things are.
So let's just start with that big question. When you ask an AI to find a cat in a picture, or translate a sentence, how does it decide that's a cat and not, say, a toaster, or that bonjour means hello? What is actually happening inside that digital brain to make that final decision?
It all comes down to something called an activation function. Now, the best way to think of it is like a little gatekeeper, or maybe a bouncer, standing at the door of every single neuron. It looks at all the information coming in, and then it makes a simple choice. Should this neuron fire and pass the message along, or should it stay quiet? It's like a tiny dimmer switch, controlling the flow of information that ultimately shapes the AI's final answer.
Okay, so to really get a handle on these things, we have to start at the very beginning. I mean, what's the absolute simplest way a neuron could possibly make a decision?
You see, every neural network is up against a fundamental challenge. It has to make sense of a world that has both simple, straight-line patterns and really complex, tangled-up patterns. The big question is, how can a single system possibly handle both of those things?
So, what's the most logical place to start? Well, with a straight line, of course. Let's take a look at the very first attempt at one of these activation functions, the simple but, as we'll see, pretty flawed linear function.
And here it is, a linear function. The equation is beautifully simple. F of x equals x. That's it. Whatever number you put in, that exact same number comes right back out. It's a perfectly straight, totally predictable line. It's simple, it's clean, but it's also a little too simple for the real world.
So why is this a problem? Well, for a few big reasons. First, because it's just a straight line, the network can't learn from complex mistakes. It's kind of like trying to aim better, but you only have a ruler to guide you. You can only adjust in one rigid way. Second, if you stack a bunch of these linear layers on top of each other, you just get one big linear layer. It doesn't add any new learning power, which totally defeats the purpose of a deep network. And ultimately, it just can't handle the messy, curvy, complicated patterns of real-world problems.
So, the total failure of that linear approach? Well, it actually forced a major breakthrough. AI needed a whole new kind of function, one that could actually bend and curve and adapt. And this was the nonlinear revolution, the key that finally unlocked the real power of neural networks.
And this is why that breakthrough was so important. Just look at this. Does that look anything like a straight line to you? Of course not. This is what most information in the real world looks like. It's messy, it's curvy, it's, well, nonlinear.
And this is the absolute core concept right here. Nonlinear functions give a network the flexibility to bend and twist its understanding, which lets it learn these super complex connections in data. This is what allows an AI to see the subtle patterns in an image, or hear the tone of a voice, or understand the action in a video. It's how AI actually learns to model the world we live in.
Okay, so we know we need nonlinear functions. Now let's go ahead and meet the all-stars, the most common and powerful activation functions that are used in AI today. First up is a true classic, the sigmoid function. Sometimes you'll hear it called the logistic function. This was one of the originals, and it is fantastic at one very specific and very important job. So, its superpower is taking any number you throw at it, positive, negative, huge, tiny, whatever, and neatly squishing it into a range between 0 and 1. This makes it absolutely perfect for predicting a probability. You know, is there a cat in this image? A sigmoid function might spit out a 0.95, which basically means I'm 95% sure there's a cat. But it's not perfect. While that clear probability is a huge plus, sigmoid has a pretty major flaw, something called the vanishing gradient problem. So imagine you're trying to train the network, right? You're sending feedback from the end all the way to the beginning. With sigmoid, the further back that feedback travels, the quieter it gets, until pretty soon it's just a whisper. The neurons way at the beginning of the chain, they can't even hear the feedback anymore, so the network just stops learning. It's a massive problem for really deep networks. All right, next up in our lineup is Tanh, which stands for hyperbolic tangent. The easiest way to think about this one is as an evolution of sigmoid. It's like its slightly more centered, maybe slightly cooler cousin. So the big improvement here is that its output is balanced. It ranges from -1 to +1, and this means the data getting passed between the layers is centered around 0, which actually helps the network learn in a much more stable and efficient way. The downside? Yep, it still suffers from that exact same vanishing gradient problem. That learning signal still fades away in deep networks. All right, it is time for the modern champion, the undisputed king of activation functions in pretty much most deep learning applications today, ReLU, which stands for Rectified Linear Unit.
So why is ReLU so incredibly popular? Well, first off, it is lightning fast. The math couldn't be simpler. If the number coming in is positive, it just passes it through. If the number is negative, it just outputs 0. That's it. This makes networks way faster to train, and it also avoids that whole whispering gradient issue. But it has its own unique problem, the dying ReLU problem. A neuron can get knocked into a negative state and then get stuck there, always outputting 0. It's basically like a light switch that breaks in the off position and can never ever turn on again.
Now, to solve that dying neuron issue, researchers came up with a simple fix called Leaky ReLU. It's a tiny change. It just allows a very small non-zero signal to pass through for negative values. This essentially keeps the neuron alive and able to learn. And then there's softmax, which is crucial for a totally different job. When you need to choose between more than 2 options, like is it a dog, a cat, or a bird, softmax takes all the network scores and turns them into a nice set of probabilities that all add up to 100%.
Okay, so that's a whole toolkit of different functions, and this is really where the theory hits the road. How do we actually go about choosing the right tool for the job?
This is it. This is the practical question every single AI developer has to face. With this whole menu of functions to choose from, how in the world do you pick the right one for your specific project?
Well, a really good place to start is with a cheat sheet, something just like this. It lays out all the key trade-offs at a quick glance. You can see the output range for each function, whether or not it's centered around 0, and the big one, is it vulnerable to that vanishing gradient problem? This is a fantastic way to quickly compare your options side by side. And here is how you put it all into practice. This is pretty much the standard playbook. For most of the hidden layers, the middle parts of the network, you are almost always going to start with ReLU. It's fast and it avoids the gradient problem. Then you choose your final output layer based on what you're trying to do. Is it a simple yes or no question? You end with a sigmoid. Are you choosing one option from a whole list of categories? You end with softmax. It's a really clear and powerful guide for building effective networks.
So we've seen this whole evolution, right? From simple straight lines to this really sophisticated toolkit of nonlinear functions that power the AI we see today. But as we all know, technology never ever stands still. So that leaves us with a final, pretty big question to think about. As AI starts to tackle even more complex, more nuanced problems, what new challenges are out there that will demand a whole new generation of these decision makers for the AIs of tomorrow? Something to chew on.